Good morning, good evening.
Good morning.
Let's start. Last week I couldn't take classes because I was not well, and in the middle of the week I had to travel to Hyderabad. So a lot of uh, things for the last 2 weeks, because of which I couldn't really take classes. Only one class for the last 2 weeks I had taken, right? The two was last Sunday. Sorry, even now there is some cold. Uh, let's start. I know that there has been a discontinuity in our classes, so better to just touch upon what we had looked at earlier. We were discussing LDOs. Do correct me if I'm wrong, if I missed something. We are discussing LDOs, and let me just share the screen. Let's quickly go over the revision. Okay. These screenshots are from last to last class. To almost 3 weeks ago class. Okay, so here we were discussing on the LDO and why an LDO is required. First thing, the battery voltage is not really regulated. It can vary between a huge range. Let's say a battery is rated 3 volts, but it can vary anywhere between 2.5 to 4.5 volts. Sometimes it is not at all in your hands. If it is not in your hands, then it's better to take it into your hands and then make sure that you have a regulated voltage generated out of the battery. Let's say you have a 3-volt battery, you generate 1.8 volt regulated, or a constant 1.8 volt battery, 1.8 volt supply internally. Let's call it V out or VDD, right? The dropout is basically from supply. What's the difference? Supply to output difference is called the dropout. And although this says low dropout regulator, sometimes it need not be very low dropout. We still call it LDO. Typically low dropout, meaning if you go to the latest technologies, your supply is somewhere around 1 to 1.2, or at max it could be 1.8 to 2 volts. But internally, even if your battery supply is 1.2, 1.3 volts, internally you generate a supply of, let's say, 0.9 to 1 volt. The drop is very, very low there. There it is apt to call it as LDO regulator. But with the higher nodes, higher technology, where the supply V battery voltage is higher, it may not always be low dropout, but it is a regulator for sure. But there is no distinction between when to call something an LDO, when to call something just a regulator. There's nothing like that. We can still call it LDO regulator. In short, we just call it LDO. Okay. So the output has to be irrespective of the supply variation or irrespective of the load variation. We don't know the load, right? It could be just a capacitive load. It could be just a current load, whatever the load you connect. The output has to be regulated at all times. That's what a regulator or LDO is going to do. Then we started looking at, deriving some things. For example, I just took the output stage of an LDO, where you have a PMOS and 2 resistances. Then we clearly told, okay, if there is a current I flowing between R1 and R2, if we can, let's say, somehow regulate one point, let's say the drop across the resistance R2 to 1.2 volt. If this is if it is somehow regulated to 1.2 volt, the node V top will be nothing but I into R1 and R2, where I is equal to 1.2 by R2. Right? So we have a fixed I going into R1 and R2. So we have a fixed V top. We can achieve this. But it doesn't mean that the current I will also be flowing through M6 as well. The current across M6 will be the current I plus the load current. So M6 current through M6 can vary. It varies with respect to IL. And if IL varies, M6 must make some adjustments to make sure that it can give out such current variations as well. For example, now I clearly mentioned earlier that VTOP is a constant voltage because there is only one I flowing through R1 and R2. If there is only one current flowing through R1 and R2, VTOP will have to be constant. It is nothing but I into R1 plus R2. Any variable current will have to flow through IL only, and VTOP will always be constant, meaning the VDS for M6 is a constant voltage. If VDS is constant, what is the only other thing that we can have for the variable current? It is a gate voltage, which is Vx in this case. So for any change in IL, Vx has to change. How? If IL increases, Vx has to decrease. Why? Because we have to accommodate more current in M6. So IL increases, the current across M6 increases, and hence Vx has to come down. Similarly, the other way. Right? So there are two things here. If we can achieve the VFB node constant at 1.2, and we can make some adjustments to Vx with the varying IL, we'll be able to achieve a regulated voltage VTOP. VTOP will be regulated voltage if these two could be achieved. And how are we going to achieve that? By having something, a circuit like this, where FB node is given in negative feedback. And because it is in negative feedback, it will follow VREF because of the virtual short property of any negative feedback circuit. So VREF and VFB will start to follow each other. So VREF increases, VFB also increases, but in this case, VREF is a constant voltage and VFB is also a constant voltage. And it may vary here and there, but in the steady state, for the DC operating point analysis, you can consider FB to be equal to VREF, which is 1.2 volt here. So now we also analyzed how IL increase. What happens if IL increases? If IL increases, Vx has to decrease. We could also achieve that, and we did analyze this as well by breaking the loop, and we analyzed how our loop is in the negative feedback, and hence we are able to achieve that Vx variation as well, along with the if IL varies, Vx also varies here. So we could achieve both things. One, this constant 1.2 voltage, 1.2 volts at FB. That's one. Second one is a Vx variation inversely proportional to IL. Even we could achieve both. And clearly we understood that the VTOP voltage or Vout voltage here would be 1.2 by R2 into R1 plus R2. This is the equation for the Vout. Right. Then we started looking at the poles and zeros, what happens to poles, and what is ideal output voltage. Ideal output voltage is V out by Vref is 1 by beta. And that could be achieved only if the value of the open loop A is very, very high. A stands for A1 into A2, A1 into A2. If A is very, very high, we can achieve that transfer function of 1 by beta. If A is not very big, then there will be a 1 by A factor coming into picture. Eventually, your V out by Vref will not follow the required ratio. You will not get the required output, and there will be some inaccuracy. So that's the reason the gain A has to be as high as possible. Note that A is the open loop DC gain that we are talking about. It has to be very, very high. The higher it is, the better it is. As we had referred to the Miller compensation earlier, and then we started looking at what happens if the Miller is added. How does our response look like? Let's go here. Let me just show this graph. Let's say we have typically the red graph here, where omega V out being one of the pole. We considered that as a dominant pole. It need not be always the dominant pole, but for the sake of consideration and discussion, we took omega V out to be the output pole, omega X to be the non-dominant pole. Then if red is the waveform or the red is the frequency response that we have, there are two poles inside UGB. One is omega X and omega V out. We do not want that. How can we make sure that there is a single pole? Why? We have understood earlier, a single pole will be the stable system. If there are two poles, it is highly likely that we are in the edge of instability, or possibly we are also into unstable condition already. So we have to be very careful there, having two poles inside. So we'll have to have a single pole. So how can we do that? Can we reduce the DC gain? That's what the black curve shows. The black curve shows that the gain, if reduced, our UGB will be inside and omega X is outside. So single pole, right? It's effectively a single pole system, having only one pole of omega V out. Omega X is already outside UGB, and hence we are safe. It helps us to have a positive phase margin and hence stable. But it need not always be true. One thing here is that we are reducing the DC gain, and because the DC gain is reduced, the accuracy takes a hit. So you clearly saw that the A has to be as high as possible. Now we are trying to reduce A by a significant margin. The moment you try to reduce A, your accuracy is hit and you do not want to have that. What's the alternative? Alternative would be to somehow have stability by using compensations, and that compensation is a Miller compensation that we discussed, where we put between the output stage, input and output, we just put a Miller compensation CC. And now there are new problems getting introduced. Because of CC, we saw that the poles, omega V out will move out, omega X will move in because of the Miller effect. But at the same time, we are introducing a zero. That zero is given by, what's that zero? Zero is given by GM by CC. That's another new thing that got introduced. Now that zero can create some problems, especially that being the right half plane zero. Now, we did look at what is right half plane zero, what is left half plane zero, what are right and left half plane poles. Typically, almost all the poles lie in the left half plane. Zeros could lie both sides, one on the positive and one on the negative. We would like to have every pole and zero to be in the left half plane. Why? Because if the zero is in right half plane, although slope wise we do get a benefit of plus 20 dB per decade slope, we have a problem with respect to the phase, because even if there is a zero, it gives the same phase degradation as that of a left half plane pole. We do not want to have this right half plane zeros minus 90 degree contribution. We do not want to have it. We somehow would like to move it to left half plane zero. If we can move it to left half plane zero, the phase benefit is what we can get. Now, because the phase is 90 degree, what's going to happen is, you see, effectively there is the first pole and the second pole. Just around that, you could have a zero, which is, you see, there is a second pole, and post that there could be a zero that we introduced. Let's say the black one, the right half plane zero, was initially there. Although the slope becomes better, you see the slope is, just added by plus 20 dB per decade slope. You added the slope, however, the phase has gone bad. So overall shift in the phase is 180 to 90. The second pole contributes another 90. The zero contributes another 90. So meaning whenever you cross UGB, the black line is the UGB. Let's take that. Whenever you cross, sorry, it's not UGB, it's a zero gain line. Okay. So whenever you cross the zero gain line, 0 dB line, gain equal to 1, 0 dB line, you see that your phase is already around 0 degree, meaning your phase margin is 0. You do not want to have that, and hence you would like to move your 0 to the left half plane. If you have moved to left half plane, what happens is, depending on where the 0 is, whether it's a 0 first or the pole first, if it is 0 first, then you will have the blue curves. You see that the phase will always settle to somewhere around 90 degree, meaning the phase margin will be 90 degree. If you have another case, which is the green case here, where the pole is first, 0 comes later. Even then, because now the 0 is a left half plane 0, it is contributing to plus 90 degree of phase shift. The phase which is supposed to fall at the pole location, it immediately recovers and then it settles to plus 90 degree. If you look at the UGB, you will see that it's always plus 90 degree of phase margin that we have. So all the time, right half plane 0 is not good. Left half plane 0 is good. Okay. So left half plane 0 is what we try to achieve by introducing a resistor RZ. Now, earlier our 0 equation was GM6 by CC. Now 1 by GM6 becomes minus RZ. There is an RZ that gets introduced. And with the value of RZ, you can control the location of the 0. Ideally, you would like to cancel your second pole, which is your omega V out. It's GM6 by CL. You would like to cancel this with this pole, this 0. GM6 by CL is equal to 1 by CC into 1 by GM6 minus RZ. So you can get a value of RZ and make sure that RZ is greater than 1 by GM6 so that you can move your pole into left, your 0 into left half plane 0. So that your phase margin is always improved. Okay. Yeah, this was from the last to last class. But let's also look at what we discussed in the last class that we had. We started looking at some more details of two-stage op-amp. In the earlier class, we looked at the stability part, but now we have to also look at various other specifications such as slew rate and let's say ICMR, CMRR, other things as well. We started discussing on the same two-stage op-amp with a Miller compensation. We started discussing the slew rate And in the slew rate, we figured out that, okay, what is slew rate? When the slewing happens, and during slewing, who is controlling the current or who is limiting the output ramp up? Slewing meaning the output is raising from first state, let's say 0 volts to a higher voltage, right? So here, who is limiting it? There are two limitations, one being the current through I6 limited by the capacitance CL. If the capacitance CL is very, very big, that could be one of the limiting factor as well. Second limiting factor is how fast does CC charge? First thing, why should CC charge, right? CC charge or discharge. This CC is one is a capacitance which is also connected to Vout node, and CC is what current we can take out or what current we can push into CC. It depends a lot on ISS. So basically, if you look at ISS is the only current that could be taken out of CC, pulled out of CC. Hence, there is a current I6 which is being pushed into CL, I6 by CL or ISS by CC. Minimum of this is the slew rate. Who is limiting? Ideally, it will not be the CL because the driver M6 is very, very strong. And typically M6 can handle very high currents, and hence the capacitance CL, it can get charged quickly, but the limiting factor will be now the CC, because CC can only, there is a fixed current that can be pulled out of CC, which is ISS only. Then we started looking at some analogy on the driving and the LDO. Then we also decided that let's go ahead and design the circuit. The calculations are all here. We started designing right from with all the equations that we know. We started designing right from the currents that were given. We have some specifications that are given in the left. Slew rate is given. The DC current, I quiescent current of 250 microamps is given. A lot of specifications are given, and then we went ahead and then derived the sizing as well for all the transistors that are present here. Right. I am not sure if you have implemented this on Cadence. You had good amount of time thanks to last week no class as well, so you had more than 2 weeks. Any difficulties? Could you implement this on Cadence? Anyone? Okay. Yes, I understood that you're not, but if you have to be, if you have to get thorough with analog engineering, analog design, you have to go back and then work with Cadence. If you do not do that, only theory is never enough for analog. I can give you that. Please go ahead and implement it on Cadence, and then only we will be talking further details on that. Okay, I do want to know what are the problems that you face so that we can solve it. Anyways, then in the last class, we also started looking at the accuracy point of view. If you have to be very accurate, what is that you have to do with the circuit? And there are some simulations that we look at. Those are called Monte Carlo simulations. Monte Carlo simulations will give you a rough idea on how much of variation your circuit can see on silicon. It is the worst case variation that you can see. Monte Carlo, what it does is it randomizes the parameters that are used for the simulations. Every device has some parameters associated with it, and these parameters are randomly varied. And with the randomly varied parameters, what's that output that you get? For example, if you look at an LDO with an output voltage of let's say 1.8, the distribution 1.5, let's take the same example that we discussed last time, 1.5. So if you do 1000 simulations, Monte Carlo simulations are that way, they are done in bulk. Typically we would require something like 1 into 10 to the power 6 simulations, but because we will not have time or will not have the simulation space, a lot of disk space it consumes, so we will limit, we can limit sometimes to, let's say, 1000 runs or so. It depends from company to company what amount of simulations you do. Say 1000 simulations are also done quite commonly with 1000 runs. You all the time you calculate what's the output. Let's say 1.5 is what you required, while 500 of them fall in the bracket of 1.5 plus or minus some delta. Some corner cases will fall in the extremes of 1.2 and 1.8. It is going to happen if your design is not really very good. If your design is good, if you have made sure that all the issues are taken care, especially with respect to the mismatch and variability, then your distribution may be tighter, meaning earlier it was varying between 1.2 and 1.8. Now it could be 1.4 to 1.6 only, depending on the accuracy that you have. Okay. Now, how do we know which device is causing the issue in case there are a lot of variations? That will be done using DC match simulations. There is a simulation called DC match. It's also there in Cadence. It's there in EdSpice. It's there in every simulator that you can use. This DC match simulation, what it does is it has an algorithm in the background, and it takes the maximum random variation that a Monte Carlo simulation could have given. It takes one combination of the, let's say, parameters, and then it tries to get you the information on who is causing the maximum variation at the output. Let's say in the output you saw 1.5 varying between 1.2 to 1.8. That's a huge range. And then I'll come back and tell, okay, M1 and M2 being the input transistors, they contribute to 20% each. 20% each is a contribution for the overall variation in your output, meaning M1 and M2 being the maximum contributors for all these issues. You would like to make sure that this contribution comes down. 20%, 20% becomes, let's say, 5%, 5%, or ideally you would like to reduce the contribution. There is a parameter called AVT. Your variation of the VT is directly proportional to AVT. The more the VT varies of your devices, more is your distribution width. You would like to reduce this distribution width. So VT variation is directly proportional to AVT. You somehow would like to reduce the VT variation. That could be done by, you see the lower expression, VT variation is directly proportional to AVT divided by root of W and L, W into L. So you increase the area. You are going to get lesser variations, and you have to make sure that there is always a catch about how much you can how much you can increase the area of the input transistors, because it shouldn't cause some other issue. It shouldn't cause a bandwidth degradation because there is an extra cap that is being introduced at the input of the op amp now, right? But in most of the circuits, you can increase it. Let's say earlier the sizes was 1 by 1. Just giving an example, you can typically increase it to 10 by 10. Even that's very much allowed. And usually you may not see a lot of negative effect on your circuit. It will still work fine. With that, you will be able to reduce the VT variation by, let's say, 10 times, which is a very significant number. Yeah, that's what we had discussed. We took some good amount of time in the last class regarding the design. This will only be good if you implement it on Cadence. Let's see if I can connect to VPN and then see if we can take these sizes, implement them on Cadence. Give me a minute while I try to connect. Yeah, it got connected. Okay, I'm able to open it for reading. Give me a minute. Okay. Let me know when you can see it. Maybe share the screen. There is some. Able to see it? Okay. So this is the circuit that I had built earlier, and we'll reuse the same thing. Probably just put the sizing in place, and we must be ideally able to see it. Ideally able to see the output. Let me share the entire screen so that I hope you can see the screen now. Yeah. Okay. So we decided that we have the sizings here. We will just go ahead and implement the sizing, whatever we have discussed. We'll go ahead and implement it on Cadence. First thing, IRF being 5 micro, the output being 1.8. Sorry, 1.8 is a VDD. IRF, this is IRF I source I have instantiated. Hopefully you're familiar now with the instantiations of the sources and things. Just 5 micro, and this transistor is lower transistor, this one M0. Let's go to M0. Where is M0? 5 micro. W by L is 1. So what should we do? So let's say length. I'll just keep length to be 1 micro. Let's just see it. This is also, it's 1, right? So 1 by 1 is what I have kept. So here for this, what should be the thing? It's 25. If M0 is 1, M5 is what? M5 is 5 times, right? M5 is 5 times. M5 is W by L is 5. So it is length is 1 micro. This is 5 micro. And this is length is 1 micro. And width is what? That's M7, 16. Right? 16. M7 is 16. So let's just put it as 16. So there is an upper limit of 10. So in that case, what we have to do is let's put it as 8. And there is something known as multiplier. Multiplier is nothing but same replication. How many replications would you like to have for the same transistors? So width is 8 micro into 2. Overall, it will be 16. 16 will be our W by L. So I have put, so the lower transistors are all done. We have to now talk about the input transistors. Let's go back to the input transistors. What are input transistors? M1 and M2. Where is M1 and M2? M1 and M2 is here. It says 1.1. Right? Let's go ahead and implement, let's say 1.1 at the input. 1.1. If for this is for input transistors, we need not have something like the higher length here. Let's say I'll put 200 nano as length and 220 nano. 1.1 is a factor, right? Okay, it doesn't allow 220 nano. So it is minimum is 320 nano. So what we'll do is 300 and 330 nano. It's 1.1 times, right? So 300 into 1.1 is 330 nano. Similarly here, 300 nano, 330 nano. That's also done. Let's go to the top PMOS. Top PMOS are M3 and M4. 4 is the ratio. Again, you need not have the minimum length. Or you need not have longer length. However, this is a current mirror. If you see, this is clearly a current mirror. Just for the sake of having a current mirrors typically have to have higher lengths. Why? Because it gives us better resistance with the higher length. That's the reason we have put a higher length here. So it's 4 by 1 micro, 4 by 1. So W by L is 4. I've given it as 4 by 1. Similarly here. So I'm just implementing the same numbers, whatever we have calculated, just that length is what I'm changing, that's all. W by L ratio is the same. Okay, M6. Let's go to M6. M6 being, that is M6 sizing 25. Now, should it be 1 micro? It need not be. We can also have a smaller length. Let's go ahead with 200 nano petalos. And what is our length there? It is 25. 200 into 25 is 5 micro. Multiply this one. So 5 micro by 200 nano is 25. Okay. So now we have put all the transistor sizes. Only capacitance is what remains. Our capacitance size is what? We chose 2.5 picofarad. Let's come back and then put it here. Now we have not taken ideal capacitance here. We have taken a capacitance which can also be fabricated. We call it MIM cap. What is MIM cap? I'll just give a brief introduction in a while. But MIM cap is something that you can fabricate. So it doesn't really allow a huge cap of 2.5 picofarad. So what I have done is I just done a capacitance of 2.5 femtofarad into 1000. The multiplier is into 1000. That will give you 2.5 picofarad. Okay, I just put it. What else I have done? I have given a reference voltage. Yeah.
I have a question. This capacitance again, it is in the reality it will be a length and width of the
Correct.
mass.
In it need not be MOS. It is not always MOS. This is a this is MIM cap being. I'll give you a brief intro of what MIM cap is in a while. But yeah, in reality, it will be some dimensions of some device or some metal or anything like that. So it is just width versus length into 1000. 1000 instances of some structure which is replicated 1000 times. So this gives us the freedom of calculating. Let's say, what is a calculated, parameter would you like to calculate? You can give length and width and then tell it to calculate the capacitance. You can you can give capacitance, and then one of these three will be auto calculated. The other two parameters you can give. So that's what this calculator does. So here what we have done is we gave capacitance and width, and length is what it calculated.
It calculates. Fine.
Yeah. Now there are some more things that we have here which probably we had not seen earlier. One thing is there's a load capacitance. Do you remember what I mentioned? The load capacitance CL is 10 puff, and I do have 10 puff here, 10 picofarad. And post that there is a feedback given. You see V out to VFP. There is some structure in between which is called I probe. Now, in any of the AC analysis, we have to break the loop and then analyze. That breaking the loop is done by this I probe. We'll see that. I'll also tell you what I'm talking about. But this completes the loop V out to FB. There is a loop, and you remember, because any open loop OTA or open loop op-amp may not have a stable operating point. Even with the slightest change with the input, your operating point varies a lot. So to make sure that we have a stable operating point, we have to give a feedback. That feedback gets completed by this I probe. Okay, now if you look at any system, any AC system or any loop, you have to ideally calculate the loop response or the AC response. How do you do that is typically you break the loop somehow. This is your V out. You would like to break the loop somewhere, and ideally once you break the loop, you are supposed to give an AC signal here and see what amount comes back here. That's your AC response, right? You give an input here, AC input, and see how much amplified does it become. That will give you a gain A. Gain of the system you will see at the output node. Now, there's a catch here. One thing is, for any AC response, your DC operating point has to be set. Meaning, you cannot randomly break the loop here, disconnect the wire completely, and then give a AC input here. It doesn't work that way, because your DC operating point is not really fixed. DC operating point gets fixed only if there is a feedback. What I mean is that if you have to first establish a feedback, you have to set the DC operating point. Once the DC operating point is established, then only you will be able to you have to give the AC input. Meaning, let me clear all the drawings. You have the CFB node coming here. It's a feedback, right? Now, you cannot randomly break the loop. So what you're supposed to do is, let's say you have this V out here. You have to pass the DC so that your DC operating point is not really disturbed. So you pass the DC. So inductor has this characteristic of passing the DC, but blocking the AC, blocking high frequency components. So I do this. So only DC operating point passes, but whenever a high frequency signal is applied, it blocks it. Now, we have established only half things now. That meaning only the DC is being passed. Where is AC applied? We are yet to apply an AC signal. Now, go ahead and apply an AC signal. Now, why this? Because again, it blocks the DC. There is no DC signal coming into the AC source here. It is completely blocked, right? Whatever the AC that you apply here will directly be visible on the other side of capacitance. Why? Because capacitance passes the AC input. Capacitance passes high frequency components and blocks the DC. So we use L, let's say L equal to infinity, C equal to infinity. You can use L and C and an AC source. Here, now what happens is, now during the initial simulations or initially any AC simulation is nothing but DC plus frequency response. So initially it will do a DC simulation. When it does DC simulation, all the DC operating points are set, and on top of which the frequency response is calculated. Now the DC is set as the inductor passes all the DC voltages. Post that, once the DC is done, now the frequency response starts. For that, your AC source will get, AC source is being enabled, and the capacitance just passes the input, AC input, to the input of the op amp, and we will see the output at V out node, which gives us the gain at high frequencies as well. Now, you can do this in the same setup of inductor, capacitance, and AC source, run a AC simulation. Or there is a second way where if at all you have to look at the AC performance, which is nothing but the magnitude and phase phase of the response. The second way is to go ahead with something known as LSTB, or simply it's also called stability simulations, STB simulations, where instead of L, C, capacitance, and the AC source, all you have to use is an iProbe. The tool will take care of all the setup of L, C, and AC. It will take care of it. It will do a stability simulation. It will also give you the direct values of gain margin, phase margin, and DC gain, gain bandwidth product. Everything it will give directly. So you have two options. We typically go ahead and use LSTB or STB option. Now, how do we do that? Let's go back. I'll erase everything.
LSTB is HSpace term, right?
LSTB is HSpace term. We also have a stability in cadence.
That is, yeah.
Yeah. Okay, check and save. Go to launch. Probably I do have ADL. Let's see. No, I don't have any. I was thinking if I have some older states, no problem. Let's go back and let's say set up model libraries. GPTK45. By default, it is selecting MC. Let's just select TT. There is a VREF. What is VREF? VREF is the input to the op-amp. What is the voltage? It's 1.2. So these are the variables that you can define. If you look at the voltage source at the input, I defined it as VREF. Okay. So this VREF can be later. You can put the value for VREF later as well. I have put it in the design variables. Let's go and say, what do you want to do? You would like to see the DC simulation. That's one thing. Say DC operating point. Do you want to vary something? Ideally not, because VREF is a constant voltage here. You do not want to vary anything. I'll say, okay. So DC is enabled. On top of it, you would also want to do a STB simulation. You have STB simulation here. What do you want to sweep? You want to sweep the frequency. From what frequency to what frequency? Very low frequency. 10 Hertz is also okay. 1 Hertz is also okay. Anything. It has to be a very small value. Even at 1K is also fine. There is no harm. Even at 1K, the gain will be very similar to what you get at very low frequency of 1 Hertz. Stop frequency, let's give it as 10 giga. Now it asks for a probe instance. What do you mean by probe instance? You have added a iProbe here, but schematic doesn't know it, or the simulator doesn't know it yet. So you have to go select, then say probe. Just select that. Come back. You see that the probe instance /iProbe0 is here. Press OK. Okay. Now you have this. Is there anything else that you would like to do? Probably you can add some outputs, but I need not as well. That's okay. Now you have to netlist and simulate. You can just see STB is all done. Now let's come back and see some of the operating points that we had earlier decided. You remember it was a 5 microcurrent. Okay, the 5 microcurrent is coming here. The M2 or the input stage current was what? You remember that? The current here, ISS was? Where is the value of ISS? 25 micro. Because the input transistor is 12.5, the overall current is 25. But let's see whether did we get that. According to the DC operating point simulations, we got only 21 microamps of current. It is not 25. There must be something wrong with the current mirror. Could be something more as well, but let's just for the time being think that it must be the current mirror issue, because the VDS for the left side transistor is 615, but VDS for the right side transistor is 420. Now can we go higher? We can, but probably we will not be able to, because there must be enough headroom for the upper transistors to operate. So we may not really have that freedom of going into having higher VDS here. Well, that's fine. The output current, probably it was 80 micro, but what we could achieve is somewhere around 76 micro. Okay, so we do have some offsets here and there, some off. That must be okay. Let's look at the DC gain that we could achieve. I clearly mentioned earlier that the DC gain cannot be directly calculated from our hand calculations, because we do not have an idea on the R out of the transistors. First stage out, we do not know the values. Second stage out, we do not have the values. Now, by our experience, you may come across some ballpark numbers, or you may estimate some numbers, but it may not really be accurate as well all the time. So for the time being, let's just keep it aside. Just look at the GMs of the transistors. Now, we had calculated a couple of GMs. One is the GM of the input transistor, which is what, 78.5, and the GM of the output driver, which is 785 micro. Do we have the values? Because the value of GM, GM1 and GM6, they affect our pole positions a lot. If you remember, the output pole is GM6 by CL. If GM6 is not 785, GM6 is a smaller number, meaning your output pole is now becoming near and near to the zero frequency, meaning it is moving in, and hence you have a threat on the stability part. Let's just look at it. 78.5 and 785. Let's look at the GM of the input transistor, 68. GM of the output transistor, 666. Meaning the ratio is near to 10, which is what we wanted. However, the values are not up to what we wanted. Values are different. We wanted 78 and 785. We are off by 10%. No, we are off by almost 20%. But we cannot help it here. There are ways to improve it, but we'll see that. For the time being, let's also look at the output voltage. This is supposed to be a unity gain feedback voltage buffer, meaning the input is 1.2, output also has to be 1.2. But is it the case? You see the input is 1.2, clearly because it's an ideal voltage that we provided, 1.2. On the other hand, you see the input voltage is 1.194, meaning Vout node is 1.194. Because of the accuracy issue, you do have some problems, but it's still reasonable. It is not like it has gone like 1.15 or 1.25. No, it is still under the limit, just that it is slightly here and there, but must be okay. At least the loop is regulating fine, right? Let's go and look at the results. DC results, at least we already took a short look at. Let's look at the other AC results. By AC result, what I mean is that it is the stability simulations, right? Let's go to results, direct plot, main form. Now you see there is only STB listed here because we ran only DC and STB. For a DC, it doesn't really give the DC results in direct plot form. It only gives you the STB, or let's say transient, AC, every other result it gives. So here we start looking at the STB results. We can just say, can you please plot me the loop gain, both magnitude and phase at dB20. You can add to outputs. Let's say plot. Separate it out. This is loop gain. This is phase, right? You can pull it down according to your convenience. I just put a vertical marker with V. So DC gain is what? Close to 49 dB. Okay. Now, can you identify where are the poles and where are the zeros? Let's also put a horizontal marker around. I can fix it at 0 dB. Okay. Now, where is your somewhere here is your unity gain bandwidth. Unity gain bandwidth seems to be somewhere around 3.6 megahertz. Did we have a value for that? Did we have, yeah, unity gain bandwidth has to be greater than 5 megahertz, right? So we calculated it to be 5 megahertz, or we did all the calculations using these equations of UGB equal to GM1 by CC. We have CC of 2.5 picofarad. GM1 has reduced by almost 20% to 66 microsiemens from 78 microsiemens calculated. So it is reduced by a significant amount. Hence, it's obvious that your gain bandwidth product will also be reduced. And from the results, you're also seeing that it is reduced to 3.6 megahertz, while ideally it had to be somewhere around 5 megahertz. Right? Okay, that's okay. But this is what we have got. Let's try to identify the poles and zeros. Now, what is the phase margin that we have? The phase margin is calculated at UGB. The phase margin you see is 64 degree. That's a phase. So you still have 64 degree that you can go, meaning your phase margin is 64 degree. And from calculations, what did you calculate? You had calculated that for 60 degree of phase margin, we did this assumption. Assumption was 60 degree of phase margin. And we did get 64 degree of phase margin, which is good. However, there are some issues because the bandwidth also reduced. You are in a favorable position with respect to the phase margin. If the bandwidth was 5 megahertz, let's say, I'll just move the vertical marker to 5 megahertz. You see this? Our phase margin would have reduced to somewhere around, I cannot accurately place it in between. Anyways, if that's the case, your phase margin would have reduced to 56. Now it is a good 60 plus, right? 64 degree. Okay, so where are the poles? It's
what
very
should tell phase margin more than 90 degree?
Phase margin cannot, it can be more than 90 degree, but ideally we designed it for 60 degrees.
60 degree.
Yeah. Now let's look at where the poles. It is very, very evident that there is one pole somewhere around here, right? So when the phase is 135 degree, at that position we do have a pole. It's very clear. And the first pole happens to be around 14 kilohertz. And this pole we already know it is coming from the Vx, the inner. We call it the input pole as well, although it is not the input of the entire op amp, entire two-stage op amp, but it's the input of the second stage. Now it's 14 kilohertz. This is one pole. Where is the second pole? Second pole ideally is somewhere around when the phase becomes 45 degree. Somewhere around that. 6.73 megahertz.
About this pole, how do you determine that is the second pole? This is the first pole. Is from the slope?
Okay, so it's not just the slope, right? It is at whenever you have the phase, every pole is supposed to give you 90 degree of phase shift. So exactly when the 45 degree shift happens, that's where you see at this position, your phase is 135 degrees. Meaning initially it was 180 degree. You're moving from 180 degree to 90 degree, but exactly where the pole happens to be, your phase shift is 45 degrees. That means 180 degree minus 45 degree is 135 degree, somewhere around here. This location is where your pole is. Now, second pole,
Hello.
there is
You are
already.
on mute.
Sorry? Sorry, was there some question?
No, not from me.
Okay. Okay.
Hello, Rakesh.
Yes. Yes, Jai Krishna. Jai Krishna, you're on mute. Okay. Already there was a 90 degree of phase shift, and further this. Hello. Hello. Can you hear me?
Yeah, I can hear you.
Yes,
Okay.
no.
Okay. There was a power cut, and I even messaged in the group. Yeah, somehow the Wi-Fi is still intact. Good. Yeah. Okay. Maybe we'll take a break and come back and discuss further on how do we improve the things, because there are some things that we did not meet the spec, right? We have to improve the things. Let's try and look at the improving things, and also discuss further on the curves that we are looking at. Maybe we'll take a break and come back in 15 minutes.
ഹലോ.
ഹലോ.
ആ ശശി.
ഉറക്കിലാ? ബുദ്ധിമുട്ടായാ?
ആ ഇല്ല, ഇനി ഉറങ്ങണത്ര. ഇപ്പൊ മണി എത്ര?
അതെയോ?
9 ആയിട്ടില്ല.
ആ, ആ, ആ.
ഞാൻ വിളിച്ചിട്ടുണ്ടായിനി.
അത് ഞാനാടാ ഇതിന്റെ ഈയിലായി പോയി. അത് സ്വന്തം ആയി ആ തിരക്കില് മുണ്ടിലൊന്നും കേൾക്കാം. അതുകൊണ്ട് ഞാൻ എടുക്കാത്തത്.
എന്തല്ല, നീ ആ ഗ്രൂപ്പിലില്ല അല്ലെ? അതിനെക്കൊണ്ട് നീ എന്തോ കാണുന്നില്ല. ഞങ്ങൾ ഒരു
ആ,
ഇത് എന്നെ ഇനി ഗെറ്റ് ടുഗദർ ആക്കുന്നുണ്ട്. ഞാൻ വരുന്നുണ്ടല്ലേ, ജനുവരിക്ക് ഞാൻ വരുന്നുണ്ട്.
ആ,
അപ്പൊ ഒരു ഗെറ്റ് ടുഗദർ ആക്കാന്ന്.
ആ,
അപ്പോ ഒരു 2-3 ജാഗ ഐഡന്റിഫൈ ആക്കിയാരി അരുണ്. അപ്പോ
ആ.
ഫൈനലി എല്ലാരിക്കും ഇത്
Hey, hi, hope you're all back. Give me a minute while I connect back to my actual Wi-Fi. VNC is not responding. Maybe I not reopen. Okay, we are analyzing this curve, and we figured out what is where the dominant pole is, and also we figured out where could be the second pole. The second pole is somewhere around here. You see that there is a curve. Seriously, the curve's slope changes, right? So if I just around here, somewhere around here, there is a second pole, somewhere around there. I'm not very sure of where it could be, but let me go to around 45 degrees of phase. Yeah, somewhere around here, that seems to be a second pole as well, just after UGB. So effectively, it is still a single pole system. Only one single pole inside UGB. That's what we can understand, right? But you also see that the curve straightens a little bit somewhere over here. Let me just bring the vertical marker. Somewhere over here, there must be a 0. And if you look at the phase has already gone to minus 37, minus 43, 45. Around this, there is a 0. Why do I think it is a 0? The phase has further gone bad. It has not improved. If ideally, if it was a right half plane 0, sorry, left half plane 0, then your phase should have been something like this. But it is a left half plane 0, and hence it is going down further. Give a minute, I'm getting a personal call. Yes. Yeah. If the phase, if it was a left half plane 0, the phase should have been improved by plus 90 degree, eventually going back to around plus 90 degree. Now, because the 0 that we have because of the Miller capacitance introduces a right half plane 0, which degrades the phase further, and hence you see that the phase is going bad. Now it is going further down. Now, why did I figure out that it is a 0? That's because the curve, if you look at very carefully, somewhere, let me annotate, somewhere here it is minus 20 dB per decade. Then it further degrades. It becomes minus 40 dB per decade. Somewhere around this location, it further improves to around minus 20 dB per decade. Probably if we get a slope of this curve, we can understand it better. But yeah, overall, this is how the slope is looking like. Maybe we'll see if it is possible to finally somehow figure it out. We have this. We have a derivative, right? derivative of it doesn't really show there is. Probably it's not the right measurement. Anyways, but just by looking at the curves, you can make it out to some extent. Because the curve has improved, meaning it has got a plus 20 dB per decade slope gain, meaning there has been a zero somewhere around this point. And that zero is also causing a minus 90 dB per decade or minus 90 degree phase shift, meaning it has to be a right half plane zero. Now we have to move it to the left half plane zero. How do I do that? Let's just go back to the schematic. Now, what are the problems that we identified here? Let's just list those first, and then we can figure it out. What are the problems that you have here? First thing, UGB less than 5 gigahertz. You wanted to have 5 gigahertz, but it is less than 5 gigahertz. Who is causing the issue? It has to be input GM. If input GM is improved to 78 micro or something, probably you can achieve that extra bandwidth that you want, right? Extra bandwidth up to 5 megahertz. Right now it is 3.6 megahertz. Sorry, it is megahertz. Okay, right now it is 3.6 megahertz. You can increase the bandwidth to 5 megahertz or so if your input GM improves. Is it enough if only input GM improves? There was a clear-cut condition that GM1 by C, what is that? This GM6 by CL is the output pole. Output pole has to be greater than 2.2 times GM1 by CC. Correct? Now, if you improve GM1, is it sufficient? You improve GM1, you move your UGB out. That is good. But at the same time, you will also have to touch GM6. Why? Because if GM6 is not improved, what's happening is you had a curve more or less like this, right? So you're trying to move this towards the right, meaning you're trying to move your DC gain itself moves towards the left. You improve GM1, right? So is it right? Am I putting it correctly, or is it that DC gain improves and then we move to the right? Probably DC gain also improves. Why? Because GM1 is also a part of the DC gain, right? So we looked at the DC gain. What was the DC gain? Somewhere around 40 DC gain of 49 dB. Let's try and improve it to beyond 50 dB at least. Let's see. But ideally, when you touch GM1, your DC gain also has to improve, ideally. But is it sufficient? Something else needed. We also have to touch GM6. Why? If GM6 is not touched, GM6 being the non-dominant pole or the second pole, there is a possibility that your GM6 by CL, the second pole, is now inside UGB. There is a possibility. It can happen that your GM6 is now inside UGB. And because if it becomes inside UGB, your phase margin is supposed to be what? Your phase margin is supposed to be 60 degree. If it is 60 degree, then it has to hold this relationship, right? So if this relationship still has to hold good, GM1 increases, GM6 also has to increase. Okay, so we have to touch both GM1 as well as GM6. We'll see that. Is there anything else? the current here. It's 20 micro. Can we increase it further? We wanted to have it at 25 microamps. But what we got is 21 microamps, somewhere around 4 microamps of loss. 4 microamps roughly translates to around 20%. All right. So 20% of the current is lost. Slightly less than 20%, but still 20% is lost. It's a huge number. We have to first improve this. If we improve the current, can we get better GM? Probably. Why? We can get better GM because the current improves. What is GM? GM is given by 2ID by VGS minus VT. If at all your ID improves, you are in for a better GM. Now, what is ID? It was supposed to be 12.5, but what you got was 10.3, which is approximately 18 to 20%. So straight away, your ID reduction itself could have reduced your GM. That's a possibility. Now, can we increase your ID and somehow make it 25? Maybe, maybe not. We may not be really able to reach there. But let's try and figure it out. Let me just edit some of the things here. First thing here, I mirror, current mirror, right? So the first things we try to improve is a current mirror. Why? Typically, almost all the problems may get solved because of the current mirror only. I'm going to just push this up because we'll see, we'll use something very, very trivial here. Now, what is the first thing that you have to do? Okay, so first thing you have to do. You have to do is, maybe I'll erase everything. Cannot really see it. First thing, let's improve our length. 1 micro length, although it is good, it is not good enough. You have to make sure that our length is quite high, at least for the current mirror. Let's put it at 5. Okay, so length and width both are multiplied by 5 times. Now, length is 5 times. Width, we may not be able to go up to 25 micro. So instead, I'll do that. I'll change the multiplier to 5 so that we achieve the same effect. Here also, I'll make length as 5. My width also has to be multiplied by 5. So earlier multiplier was 2. I made it 10 so that overall we achieve the same thing. Do you want to just simulate this one experiment and then check it? Let's do that. Okay. I don't know what has happened. Let's just see. The gain is still around 48.9. It was still around that 49 dB. So we have not really touched on the gain. But coming back, the DC points. Have we improved? Of course, the ID has improved significantly. Now it is 24.2. We wanted to have 25. We had achieved around 20.9 or 21 micro. Now it's much, much better. We have achieved 24 micro. Why? Because of our W and L being higher resistance and hence better current. The output current had to be 80 micro, but we are getting 83. Reason? Because of the VDS that we have. VDS is very, very high at the output stage. Because the VDS is high, we are able to see that the current is higher, but it's still okay. What's the GM at the input stage? We wanted a GM of 78.5. We reached 73. Okay, fine. Still short by a little amount, but that's fine. That's because of, what could it be because of it? Because of probably the VT that we considered for calculation is not very accurate. The VT varies with respect to W and L. Keeping that in mind, VT probably is slightly different, and because of which the GM calculated is not very accurate. 73 here, and the output driver GM we wanted 785, but we got 690. So let's see. Let's go back to the curve and see. DC gain has not improved. Why? Maybe because the increase in GM. What is DC gain? DC gain is nothing but GM into R out, or capital GM, capital R out, right? So we increase GM, that's correct, but R out should have decreased because of the increase in current. So overall, it just compensated with each other, and we still are in around the same thing of 49 dB or something. Let's go back to the curve. Yeah. Fine. Let's okay, let it be there the same way. It's 49 dB still. Let's go back and figure out where our 135 degrees is. 135 degrees is where we have the first pole. Still around 14.8 kilohertz. It's still the same. The first pole is still the same. Let's go and figure out where our UGB is. Unity gain bandwidth. Somewhere around 4 megahertz. Still not improved. Why? Still 4 megahertz. What is our unity gain bandwidth? It's GM1 by CC. What is GM1? Now we are achieving what, 70 micro divided by what is CC? 70 micro, 73 micro, I guess, by 2.5 picofarad. Okay, where's my calculator? Probably not here. That's fine. Somewhere around 73 by 2.5 megahertz. There is a 2 pi factor that is missing, right? 2 pi f is this. So divide by 2 pi we have to make, and we may be around 4 megahertz. You can calculate it. Meaning we are still, there is some scope to improve it. What's the phase margin? Phase margin is 62. We are still safe, but it has reduced. Earlier it was 64. Now it has come to 62. So it's slowly reducing, meaning we have to make sure that our second pole moves further outside. Can we increase the current further? We can, but ideally we designed it for 25 microamps. We are reaching 24.2. That's reasonably good. We'll just keep it there. Now, what the GM we got? 73 approximately. Can we have a better one? Now, you see that there are some things here. The VDS for this MOSFET is 1.2 or 1.8 minus 1.2. What about the VDS for the right MOSFET? It's higher. VDS is 676. For the left, it's 600. Right. So there is, ideally, you remember, if we want a better current mirror, we have to ideally have a very good VDS matching. That has not happened. Now, let's do one thing. These are also current mirrors, correct? And we have not really changed the length of these. Why don't we change it as well? If we change the length, what happens? Better current mirror ratio and higher, ideally higher output resistance for this stage, the first stage. because of which there could be slight gain in the DC gain as well. Let's try that, but there is no guarantee that we'll get that result because the effect on the gain may be very minimal, but at least for the betterment of the multiplication, let's have it. What did we have? 5 micro for the lower transistor. Here also I'll have the same. Saved, run. What's the DC gain? You see 50.3. There is a slight increase in the DC gain as well. Phase margin has now reduced. It has become 58 degree. You wanted 60 degree, right? There is slight issue with respect to the phase margin. That's one thing that we have to solve. But yeah, you will have to, as long as you adhere to the equations, as long as your equations are all good, probably you will have much better results every time. Although we increased the length, you see that there is some issue with respect to the VDS matching here. Why VDS is not matching? That's because we have not sized the output transistor adequately. If output transistor is correctly sized, you have to ideally get same, this voltage and this voltage have to be the same. But output transistor is not sized properly. Because output transistor is not sized properly, you have a problem with the loop. Now, because of this issue, there will be a current mismatch. You see that on the left, the current is 12 micro. On the right, the current is 12.2 micro. There is a current mismatch. This leads to some inaccuracy, some mismatches. Now, let's just understand what we have to do with this sizing. Why is this having an issue? One thing, our VTH calculation could be way off. Let's just figure it out. That's the VT for that transistor. Print DC operating points for this transistor. Now, what the VT is 491. Have we considered the same VT for our calculations? It's M6. So VT that we considered for was not really. We did not consider anything. We just considered it to be VGS minus VT of 0.2. What is VGS minus VT? VGS is 676, VT is 491. Is it 200? No, it is around 170 millivolts. If VGS minus VT, there is a mismatch here. It's 170 here. And in calculation, we calculated 0.2. If it is 170 in place of 0.17 in place of 0.2, what happens to W by L? It has to ideally increase. But what we calculated for 0.2 is 25. With 0.17, it may become around 32, 33, around that. So for the timing, what we'll do is we'll go back and then say that, okay, now we figured out what the issue is because of VGS minus VT mismatch, which earlier during a calculation we had not taken into account. We are seeing some issue. Let's go back and tell it's let's put it at 32, being 32 make 32 is what? 200 into 30 is 6. 32 is 6.4 micro. So I have increased the size. Why? Note that we increase not randomly, but we increase because we figured out there was a mismatch with the VT calculation earlier. there was an issue. And now with the updated VGS minus VT, have I done it correctly? What happens if size increases? If size increases, our VG will move slightly up. Why? Because this size is better. There is a lesser requirement for VGS now. This drop becomes lesser, so it moves up. Let's quickly simulate it. During the very initial phases, a lot of times we do this trial and error methods. Now let's see, where is our 0 dB? 0 dB is still around 4 megahertz. We still have not improved the bandwidth. But loop, the phase is somewhere around 60 degrees in the boundary now. Okay. What is GM? GM, we wanted 785. We are 800. That's good. Oh, what are we limited by for the UGB 5 megahertz? That's definitely the GM. Input GM is something that we have to take care of. Still 73. We can further increase the sizes to get to 78 micro of GM, and hence a higher bandwidth as well. We can go there. It's iterative process. Ideally, if you have the absolute value of VTH for a given W and L, probably you will be able to fix everything in one go. But I wanted to show you iteratively on how, what are the points that we can consider to finally reach to the points, finally reach where we would like to be. Right. So any question till here? I know we fixed the current mirror, that's fixed. DC gain, where are we now? 50? Yeah, exactly at 50. 51 dB. DC gain we improved slightly. UGB we improved from 3.6 to 4 megahertz. We can further improve it. And loop stability we figured out how to plot it, how to figure it out. One thing that is still open is with respect to the phase degradation. Can we put a RZ and then say the curve go up? What should be the value of RZ? Now, what's RZ? RZ has to be what? RZ has to be greater than 1 by GM, 1 by GM6. That is greater than 1 by 800 micro. What is 1 by 800 micro? It has to be greater than 1.25 K. For the time being, I'll just let's go back and give a minute. Do we have the value of RZ here or the equation for RZ somewhere? Not in this class, it was in the previous class. So anyways, I can write it back here. Okay, so it is 1 by CC into 1 by GM minus RZ should be equal to GM by, you would like to cancel the second pole. Second pole is GM6 by CL, right? So CL value we have, that's 10 pico. GM6 value we have, RZ we have to calculate. So if I have to just put 1 by 2.5 pico into 1 by 1.25 K minus RZ equals GM6. GM6 is 1 by 10 pico into 1.25 K. If you simplify this, what the value of RZ you get? 10 pico 4 into 1.25 is 1.5k minus 1.25k. So it's 3.75k the value. Let's put it and then see. I'll put, for the timing, I'll put an ideal resistance of 3.75k. So we have put a 3.75k ideal resistor. Run it. Okay. The phase, it somehow looks like it is trying to move up, but there's an immediate pole coming into picture. Where is this pole coming from now? It could be from anywhere, and even a parasitic pole could be coming into picture, but it is at a very high frequency, so we may be able to ignore it. Where is it? Somewhere around, let's say, your UGB has reduced. No, it has improved, right? UGB has improved. UGB is somewhere around 4.39 now, somewhere around 0 dB. And you see the phase is 79 degree now. You wanted 60 degree, but you could achieve 79 degree because of an extra zero that you introduced, or pole cancelling zero that you introduced, because of which you are having much better phase margin now. Looks like it is still a unity, sorry, it's a single pole system, but looks like there is a pole here, there is a pole here, right? There are two poles. This should be a parasitic poles from somewhere, which you may be able to ignore for the time being. But whatever the zero that we introduced probably is canceling one of the poles, the output pole already. And hence, we could get a much better phase margin. This phase margin is 78 degrees, 79 degrees, which is quite good, right? Any question? Okay, I believe there are no questions. So, but does your introduction of RZ nulling resistor, did it change the DC gain? No, it has not. What it has changed is only the phase margin, and mostly because the phase margin has changed because of the second pole being cancelled out by the zero, you will also get, it's more like a, you see that there is no effect of the second pole at all around UGB. Probably the UGB is somewhere here. It's somewhere between around 4.5 megahertz. Now the bandwidth is also improved because there is no effect of the second pole on your UGB. You can further improve it by increasing the GM of the input stage. You'll be able to reach 5 megahertz easily. No, it is not at all impossible. Okay, so I'm going to stop here. I wanted you to look at what we can touch, where we figure out the issues, and based on the issues we figure out, we'll also fix some of the things here and there. Any question? Okay. Let me stop this particular share. We looked at the STB simulation as well. We looked at the DC simulation. Probably what we will look at next time is more from, I also want to explore the Monte Carlo simulation. We will look at that. But before that, we'll also cover some theory and then come back. Okay. I'll erase everything. I'll stop the share. Okay. Earlier, there was a question on what are these MIM caps, right? There are various ways of realizing capacitance on the die, on the chip. We have to fabricate everything that we put in the design. We have to fabricate. So there are ways to generate caps. How? You use a MOSFET. You short all these devices, something like this. This is one terminal, this is another terminal. So this makes a cap. Make sure that you're operating in a region where, okay, this CV curve, there is something known as a CV curve. CV curve looks like this. Okay, so x-axis is V, y-axis is cap. This being somewhere around VT of the transistor. So if you're not operating around VT of the transistor, you're good to go. If you operate in the left part, or if you operate in the right part, you are safe. Your capacitance value is quite high and you get a decent capacitance as well. So you can use left and right areas to realize the cap. There are other ways as well. Instead of an NMOS, you may go ahead and use a PMOS. Now, there are other ways based on the metals. What is capacitance after all? Anything with two plates, two conductors, with insulator in between is a capacitance, right? So what I'll do is I'll say, okay, let's have two metals running parallelly. Both are the same metal layers. Okay. Now they are running very parallelly. They have a fixed width between them. Right? They have a fixed width between them. This is fixed. Give a minute. Okay. This is okay. Okay. They have a fixed width between them. Right? This is typically ruled by something known as design rules, or we do something known as design rule check, or DRC in the layout, right? So this width is governed by the design rules. We cannot just, every capacitance is C is equal to what? Omega A by D, D being the distance between them. The lower the distance, the higher the cap is. So you cannot just go and touch it. There must be a minimum distance between them. That minimum distance is given by something known as design rules, or process kits. Process design kits, PDKs, where DRC or design rules will all be listed and it will be shared. So we have to be aware of the design rules that we have, and based on which we can go ahead and have a particular width So if there are two metal lines running for very, very long, let's say, how does metal line look like? I'm just drawing a 3D, right? So there is a particular thickness of the metal, right? So they both are running parallelly for a long time or a long length, meaning there is a capacitance developed in between them, and that capacitance is given by the dielectric constant epsilon, A being the area of which they share. You see the cross-sectional area here, right? So all these both areas into the distance between them, divided by the distance between them. There are metals like this running parallelly, the same metal layers. Let's call it M1, metal 1 and metal 1. So with this, you will be able to realize some gap between this. This could be net 1. This could be net 2. If I have to draw it something like this, this will be net 1. This will be net 2, right? So there is a capacitance that we can develop between them. That capacitance is called metal insulator metal cap. So this is MIM cap. There is also something known as MOM cap. Metal over metal, meaning there is a metal and on top of which there will be another metal at a higher level. So this is metal 1, this is metal 1, which is on top of metal 1. So in between there is a dielectric, right? In between is filled with the dielectrics and insulator. Now this metal over metal caps are also there in some of the technologies. Some technologies may not have it. So you have to be aware that both are valid capacitances and both are used in a lot of places, a lot of technologies. MIM is a lot more common. MOM is also not uncommon. They are used typically. The capacitance that we realize using the metal capacitance can be slightly lower, the density, meaning it requires a large area to realize. Let's say you want to realize 1 picofarad of capacitance. By using a MOSFET, you may be able to realize it in, let's say, 10 by 10 micrometer square area. For the metals, with the MIM cap, if we have to realize the same 1 picofarad capacitance, you may require 100 by 100 micrometer square of area. It could be very, very large, but if at all it is possible, if you have space to route, you can go ahead and use MIM or MOM caps. It's up to up to what area is remaining with you, how much area you can afford. So based on that, you can go ahead and use MIM or MOM caps or even the device caps. Any question on this? Probably resistance, I had already explained about what are the various types of resistances that we may have, but capacitance, not so many options. There are only a few options here. But yeah. Any question? Okay. Now I would like you to practice on Cadence. Probably if you would like to implement the same design in Cadence, go ahead, do it. Okay. And once you do it, do figure out what are the problems that you have, what are the specs that you couldn't match, did not match. Make sure that you try to match them. If not all, at least you go towards the spec, you go to more near to the spec, so that you understand how you can go near to the spec and how you can try to optimize, and which parameter or which size you have to tweak, which what is that, what are the things that you have to understand, or what are the things that you can tweak to reach, let's say, UGB. You have to increase UGB further. You got 4 megahertz, you want to reach 5 megahertz. What are the things that you have to tweak? You cannot randomly tweak anything, right? You have to tweak the fixed things. For example, you look at the equation. The equation says it's GM1 by CC. CC, can you touch? You can, but there are implications. There are multiple things you may have to touch once you touch CC. GM1 looks like the simpler option. Just go ahead and increase GM1 if possible. It is possible, but how do you do that is up to you. Okay, so I'm not going to give some new exercise. You can go figure out the same exercise, put the same sizing, no issues, experiment, work with it, and then come back with the problems that you have faced. Maybe I'm going to stop the class here today because it has too much of design. I probably, if you do not do hands-on, it may be a lot boring. So try it out. Tomorrow we'll discuss further. Tomorrow I'll come back with some more theory part only. I'll not be doing cadence tomorrow, but theory we'll have to discuss further more. We'll discuss that tomorrow. Okay. Do try it out on cadence. If you face any issue, ping me on WhatsApp. Just make sure that you mention your name and batch. Sometimes I get messages without any information. Just people say hi, and I don't reply to those messages. So please be more specific on your batch and the name, so that I know who you are and what are the things that I can reply with. Okay. Then we will close the class here today. We'll meet tomorrow morning again. Okay, bye.